We're now going to do a series of videos dealing with angular kinematics. Earlier in this class, we dealt with linear kinematics, things moving from here to there, and we dealt with things like average speed, displacement, final speed, initial speed, and now we're going to be dealing with things that are rotating or things that are moving in circles, and there is pretty much an exact correspondence whenever the acceleration is constant in angular kinematics compared to linear kinematics. Here we have angular average speed, angular displacement, angular final velocity, and angular initial velocity. You might remember that the unit for displacement was meters. The unit for time, of course, is seconds. And that meant that the velocities previously were in meters per second. In sort of the same way, angular displacement is in radians. The time is still in seconds, which means that angular velocities are going to be not in meters per second, but in radians per second. And we're going to take a couple of videos and we're going to do some problems that deal with angular kinematics. Let's try one here. We have a Ferris wheel that rotates at a constant angular speed, and it takes 18 seconds to go around once. We want to find its average angular speed. The time is 18 seconds, so that's going to be t right there. It says that it goes around once. That is a hint to us. In other words, the angular displacement, when we go around once, is 2 pi radians. And it says that we want to find the angular speed, which is indicated by the lowercase Greek omega. If we look at our equation down here at the bottom, I think we're going to use just that portion of it to get the job done. Omega average is equal to the angular displacement divided by time. So that's going to be 2 pi radians. I'll go ahead and leave the units in there, divided by 18 seconds. In math, you might just report this as pi over 9 radians per second, wouldn't you? But in physics, we like to use decimals. So we're going to type in 3.14, or we're basically going to change that pi into a number. And when you do that, you get a number like this, 0.35 radians per second. We're looking at significant figures now. The time is given as 2 significant figures, so our answer should have 2 as well. Well, in linear kinematics, we dealt not only with velocity, but we also dealt with acceleration. And there's a corresponding equation for angular acceleration. It's down here at the bottom of the screen, compared to linear acceleration. The velocities in linear kinematics were in meters per second. This is change in velocity, isn't it? That's what the delta means. That was final velocity. That was initial velocity. The time, of course, is in seconds, which meant that our unit for acceleration was meters per second squared. In angular kinematics, the angular velocities are in radians per second. We just went through that. The time is in seconds. And so the unit for angular acceleration is going to be radians per second squared. Angular acceleration is the rate at which the angular speed is changing. So let's look at the problem here. And it says that this Ferris wheel has taken 2.2 seconds to go from rest up to its average angular velocity, which is what we found just a bit ago. The average angular velocity, shall I write it up here, was 0.35 radians per second. And it says it goes from rest. So that means that initially this Ferris wheel isn't rotating, and then it rotates faster and faster until it reaches this value. So for this problem, this 0.35 radians per second, which we calculated on the previous problem, has become our omega final. And we want to find what the angular acceleration is. Angular acceleration is a pretty easy one to remember. It's given by the Greek lowercase alpha. Here we go. The equation in the lower part of the screen, we definitely need this part of it, but I don't think we're going to use that part right there. Let's use those two parts. Here we go. Omega final is 0.35. Initially, it was going 0. Again, I will leave the units in there, and we're going to divide by 2.2 seconds. Everything that we're given has two significant figures, so I think we need to round our answer to two significant figures, and that's going to come out to be 0.16 radians per second squared.